To study whether information is eternal or not, physicists study black holes. Black holes are regions of space that enormous amount of mass are packed in a very small volume. Consider this as a neutral fabric of space-time. When a huge amount of mass warps that fabric, that's when a black hole is formed. So the very steep curvature in space-time is what happens when a black hole is formed. This is a diagram of a black hole. Here is the event horizon, and that's where if anything falls inside, is doomed forever to be sucked in and not escape. But anything that is outside can still have the chance to escape the huge gravitational pull that a black hole has. And the central point of black hole is called singularity. When Albert Einstein for the first time proposed general relativity, the consequence was that anything that falls within a black hole is gone forever. It is not retrievable by any observer from the rest of the universe. So the information lost because nothing can escape the gravitational pull of a black hole. This was in paradox with quantum field theory. According to quantum field theory, this equation, Schrödinger equation, which describes the evolution of the wave function of a system, if you have the state of a system at a certain time, you can find its state at previous times. Therefore, this equation doesn't prevent us to retrieve the information from past. If we have the information right now, we can retrieve the past information. This is in contradiction with what we saw about information being lost in the black holes. Stephen Hawking in 1974 applied quantum field theory to the curved spacetime around a black hole and predicted that black holes are not entirely black but emit radiation due to quantum effects near the event horizon. What does this mean? According to quantum fluctuations in vacuum, particles and antiparticles get produced and they get annihilated. So the net effect is zero. That happens all the time, and if that happens all the time, it can happen at the event horizon. But there is a chance that particle and antiparticle could have different fate depending on where they form, depending on their trajectory. If one falls within the black hole and one escapes, the escaped particles are going to look like bright radiations for an outsider observer for the rest of the universe. So the particles that fall in, let's say they're doomed, and the one that escape, they're still observed by outsider observers. And that's what is called the Hawking radiation. Interesting fact about this is that for an observer that looks at the black hole from far away, they would see the Hawking radiation as positive energy. Well, for a particle, an antiparticle, when they're formed, we know that the energy is conserved, meaning that it is zero. When energy is conserved and it's zero, if only the curvature at the event horizon guides one particle within the black hole and the other one outside, then the one that goes outside is positive energy, let's say +1, and the one that goes inside is -1. So their net energy is zero, just like vacuum. And every time that Hawking radiation happens, black hole gets shrunk because there are negative energy fallen within it. So the mass is lost. Hawking proposed that because we are putting negative energy to it. So mathematically talking, you're putting negative energy to it. Therefore, we are reducing the amount of energy in a black hole. And so the event horizon is going to shrink over time. By this, Hawking still thought that the information is lost because this radiation, this particle emitting from the event horizon still had nothing to do with the ones that fallen within the black hole. And over time, the black hole would evaporate and so information is lost. But there came Gerardus Hooft and Leonard Susskind, and they thought this is still in contradiction with quantum field theory, and therefore they proposed holographic principle. According to holographic principle, information contained within a volume of space is encoded at the surface of that volume. By that, when this Hawking radiation happens and the event horizon shrinks over time, because the information trapped in a black hole is encoded at the surface of the black hole, and we see that over time it's getting shrunk, the event horizon getting shrunk, and we see these radiations happen. They concluded these radiations, or those encoded information that are now transformed and dissipated to the universe. So they are available, but there must be a way to retrieve them from that scrambled format. And so by that, they concluded that the information is not lost, it's eternal. However, this theory is still under debate among the physicists. Is information lost forever when fallen into a black hole, or is there a way to retrieve the information when a black hole gets evaporated? Thank you for watching.